Okay, our little bonus lecture in lab. We're going to talk about some of the nomenclature stuff so that we can get started on working on our nomenclature worksheet. Remember, we talked about ions, we talked about polyatomic ions. I even had skipped ahead and we talked about oxyanions. So the names that go along with the chemical formulas is where nomenclature comes in. Nomenclature just means how do we name compounds. It more like etymologically breaks down into a crying list, but crying like the boy in the corner of the street in the New York old-timey movie that's yelling, extra, extra, read all of that. That sort of crying, like yelling stuff, announcing stuff, naming stuff. Not like boo-hoo, weeping, sad crying, but it sometimes will make you feel that way. So that's nomenclature. We're going to talk about it. There are different naming systems for different types of compounds. We are learning a very select subset of types of compounds that we're going to name. If you take more chemistry in the future, you're going to add to that, and you're going to add other systems on as well. When we are naming compounds, the most important step is the first step. It's identifying the type of the compound, because the type of compound that it is determines which of our three naming systems we're going to work in. If you don't have the identity correct, if you don't figure out what classification, which box this chemical in, you're not going to get on the right track, and it's going to be wrong. Some compounds are also going to have common names, basically just water and ammonia. So water is H2O, ammonia is NH3. There's also systematic names for these, but we're typically going to call them by their common name rather than their systematic name. So H2O is water, you should definitely know that. And NH3 is ammonia, that's also another good one to know. It'll come up less than water, but still it will come up. Our first type of compound is ionic compounds. We already know what ionic compounds are because we've talked about it. What is an ionic compound? How do we identify an ionic compound? Metal and non-metal, or more generally, ions. Positively charged ions, cations, positively charged, and negatively charged ions, anions. So anytime you have a metal and one or more nonmetals, the compound is ionic. So metal and nonmetal. It's also possible that we could have ammonium, which is not tasty, but is the NH4 plus ion. So NH4 plus is ammonium. It's related to ammonia, NH3. Instead of ammonia, it's ammonium. So NH4 plus is also a cation, but notice that there's no metals in there. So that's the one weird exception. I don't think it comes up during my slides. I don't think I've ever used it as an exam question either. Okay, so metal and nonmetal means that it's ionic, and we've got two categories, ways that we can name ionic compounds. They're sort of the same category, but it may be helpful to think of them as two different categories. So it depends on the metal in the compound. We've got basically two types of metals. We've got ones that can form only one possible charge. So that's going to be our alkali metals, our first column, our alkaline earth metals, our second column, second group. It's going to be our aluminum, and gallium also forms a 3+ charge, right? So 3A is going to be 3+. And then we've got the staircase from aluminum down to silver. So aluminum's the 3+, it's the top step. Stepping down 1, 2+, zinc. Stepping down another one, Ag, silver, is a 1+. So those are going to be all of our cations that have only one possible charge. We also have cations that have more than one possible charge, and that's basically the rest of the transition metals and some of these really low main group metals like Sn, tin, and Pb, lead, also show up in there. This is also in the slides. So for metals that form only one type of cation, meaning that every time that we see it, we know with certainty it's this, whatever charge it is. So any of these, it's just the element name with ion after it. Any of our 1A, 2A, 3A groups, 1A, 2A, 3A, as well as zinc and silver, always the same charge every single time. Just memorize the one, and we're done. So for example, Zn2 plus is the zinc ion. Question? Smells like gas. One sec. It is important that we include the ion part. The ion part of the name is important, especially for our metals, because if we just say zinc, we're going to think it's just Zn. Zinc is Zn, zinc ion. Zn2 plus. Same idea for all the rest of these metals. Magnesium is just Mg, magnesium ion is magnesium 2 plus. So it's important that we distinguish, that we add in the ion part for the name when we're talking about the ion by itself. So metal name, element name, plus ion for all of those. We also have the metals that can form more than one type of cation, more than one possible charge option that's positive. So for these, we typically use modern Stock notation, which is named after Alfred Stock. And we say, thank you, Alfred Stock. Thank you, Alfred Stock, for reasons that we'll see very shortly. So the Stock nomenclature is the name of the ion, the element name, followed by the charge in Roman numerals in parentheses. So this is going to be all metals that are not in that previous list, the previous slide. So things like iron. Fe2 plus is iron 2 ion. Fe3 plus is the iron 3 ion. We still want to have the ion at the end. It's a little bit less important because we are specifying by the name with the 2 or the 3 in Roman numerals. So it's a little less important that we include the ion part, but we should still include the ion part. And a brief refresher in case it's been a while since we've used Roman numerals, especially the smaller Roman numerals, since this year's Benito Bull was, of course, number 60, so it's just LX. So for our Arabic numerals, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. We'll go to 10 and we'll stop at 10. Our Roman numerals, it's me. It's what we say to our captain. We can't believe it. It's what we put in our arms to get hydrated. We don't put it in our arms. The nurse would put it in our arms. We usually don't use the, sorry, I got distracted by having fun. We normally don't use the little top and bottom things. And then VI, VII, 3 I's, IX, and X. So the letter I, 2 I's in a row, 3 I's in a row, IV, V, VI, VII. You don't really need to know 8, 9, 10, but we might as well just go to 10. Round number. So we're going to specify the charge with the Roman numerals in parentheses after the name of the metal. This is the modern notation, the Stock notation. It is easier than the old notation, in my opinion. We are still going to learn the old notation. Some of it at least. So for metals that form more than one type of cation, here's showing our two name options. We've got our element. We've got the stem or the base for that element. So iron has a symbol Fe. That's for this stem, Ferr. Copper has this symbol Cu. That's for the Cooper name start. And then for different charge options, for the modern names, we just write the name of the metal with the 2 or the 3 or the 1 or the 2 or the 4 or whatever number we have. In the old common name version, we use that stem, and then we have the ending OUS or IC. So for example, iron 2+ is the ferrous ion. Iron 3+ is the ferric ion. So we've got the OUS ending, we've got the IC ending. OUS is the lower charge ending, and the IC is the higher charge ending, the higher number ending. Other than that, there's not really a pattern. So if we look at our different options, ferrous is 2+, ferric is 3+. When we move to copper, cuprous is 1+. So instead of being 2+, now it's 1+. That's different. And our copper 2 is 2+. But if we move to tin, which has the symbol SN, now we're using the STAN base name, or STEM. 2+ is stannous, and instead of 3+, it's 4+ for stannic. Those are basically the 3 different options for charges. It's either 1+, 2+, 2+, 3+, or 2+, 4+. Those are the different combinations. Again, the thing that they have in common is that the OUS ending is the lower charge version, the IC one is the higher charge version. Not all of the metals that can form more than one charge have these older names, but several of them do, and there are some of them that you do have to have memorized, which I forgot to talk about in lecture, but hopefully everyone's watching the video. Hi, everyone. So we've got that going for us. You do have to know some of these common names. For things like ferrous and ferric, those would come up if you go into a healthcare profession. You're likely to see ferric and ferrous show up like in medication names. You won't see iron 2, iron 3 necessarily, so you need to know what they are so that you can identify them. This is also good because if we go back and look at old research papers, for like doing a little bit of digging around on the internet, you're likely to see these common names rather than these modern names. It would be good for us to at least know what we're looking at, even if we don't know off the top of our head that ferrous is iron 2+, because maybe it's been a while since we took chemistry. We'd see ferrous and we'd think, oh, I know that that's a chemical name thing, and then we could ask Google, hey, what's ferrous mean? That's perfectly reasonable. You'll also see some of these maybe show up on the back of like product labels if you buy chemicals or household cleaners. They could show up there. So it's good to have those. Some will be memorized. Some common names need to be memorized. Refer to your sheet of things that you have to have memorized for that. The other limitation of these common names is that we don't have common names for all the possible ion charges that exist. So some of these ones in the middle of our transition metal block can form a bunch of different charge options. Like I think manganese can do 2, 3, 4, 5, 6, and 7. And we don't have enough common names to be able to name some of those. Chromium also, I know for a fact, does chromium 6. That's an option, but we don't have like a perchromic ion, as far as I'm aware. So that's another reason why this modern nomenclature is nice. It's also just easier, generally. So those are our cations. We also have our anions. If we have anions, negatively charged ions, where it's a single element, we change the ending to "ide." And we can also include ion at the end. These ones are nice because the charges are predictable based on the periodic table. It's what we were going over in lecture. So if we're in the halogens, the 7A, those are all going to be 1 minus charges. If we're in the 6A, the chalcogens, that's going to be 2 minus. If we're in the 5A, which is the pnictogens, that's going to be our 3 minus. You don't need to know chalcogens or pnictogens. Like the name chalcogens or pnictogens. They're just fun. So for example, F minus, fluorine ion, the fluorine ion is actually F minus fluoride ion. Like shows up in drinking water, and lots of toothpastes also have fluoride in them. Drinking water if you're on city water. Cl minus is the chloride ion. Shows up in pools. Might also be in your water, maybe not good for your hair. But all of them end in "ide." Sometimes the part that we take off at the end is a little bit longer, like for oxygen. We take off the whole - igen part, so it's just oxide ion. So we need to be able to know how to do those for names. Those could also show up on our ion quiz. They should show up on our ion quiz, some of them. So when we're naming ionic compounds, we are going to be talking about ionic compounds. We're going to be covering ionic compounds that have only 2 ions. So it's a relatively simple version compared to the real world. So we've got a cation and an anion. And the name for ionic compounds is the cation name, but take off the ion part. And then you put right next to it the anion name without the ion part. That's all there is to it. So if you know the cation name, if you know the anion name, you just pop them together, and now you've got your name. The cation is going to be the first element, it's usually a metal. If it's ammonium, ammonium doesn't go first for reasons. So an example, a couple examples. We've got CaCl2. What is Ca? Ca is calcium. Calcium only forms one type of ion. It only forms calcium 2+. Cl is what? Chlorine. Chlorine also only forms one charge. It's always Cl minus. So calcium. And then chlorine, when we make it an ion, becomes chloride. So the whole name is calcium chloride. Then we've got the compound AlF3. Al is what? Aluminum. So Al, when it's an ion, would be the aluminum ion. We took off the ion part, so we're just writing aluminum. And then F is fluorine. And when we make that an ion, we take off the ene and change it to ide. So fluoride. So that'd be aluminum fluoride. Why don't you take a guess by yourself or with your partner at what KCl would be? Would anyone like to share their guess for KCl? Jeremiah? Potassium chloride is exactly right. So K is potassium. And Cl is chlorine, and we change the ending to ide, so it's potassium chloride is our name. Questions about those? So that's ionic compounds, metal and nonmetal, that have only one charge option for our cation. It's not a whole lot more complicated when we have multiple charge options. However, if we're working the other direction, it becomes a little bit more complicated. So if the metal forms more than one type of ion, the charge is determined from the chemical formula of the compound. This is not working the other direction. This is just adding on. We could have multiple charges. So for all of these, we knew what the charge is for the calcium, the aluminum, the potassium, so we just wrote down the name of the ion. Is that a question?
If we were like to do a test on it, do you care about calculus?
So that's a great question actually, because it's something that I care about. On exams, it won't show up because it's multiple choice, so you don't have to worry about capitalizations. When you're writing chemical names, are any of these capitalized? No. They're not proper names, so they don't get capitalized. Chemical names are not proper names, and so they don't get capitalized, generally. So chemical names do not get capitalized. If you capitalize them, you won't get capital punishment, but I will be a little annoyed maybe. All right, so for all of these, we knew what the charge is, so we didn't have to write it down. It will become a little bit more complicated if we're working the opposite direction. If we're working from aluminum fluoride to try to get the compound formula, it becomes a little bit more complicated because then we have to go from aluminum and think, okay, what's the aluminum formula? Hopefully we come up with Al3+. What's fluoride when it's an ion? Okay, minus, and then we crisscross. But that's about as complicated as it gets when there's just one charge option. So for our group 1, 2, and 13 or 3A metals, that's the case. If we've got multiple charge options, we have to figure out what the charge is so that we can include it in our formula. So all of these transition metal elements other than zinc and silver, and some of the ones that are below, tin, lead, some of those ones can have multiple charge options. So what we need to do is determine the charge on the anion first. So we'll find the total negative charge. And then because the charges have to be 0, total positive charge will be the same but opposite. And then we might have to do a little bit of algebra. And I forgot to write positive. So quick little example, Fe2O3. We know that Fe is iron. So if we wanted to start naming this, we can actually write out most of the name. So iron, do we know what the charge is going to be on iron? Not off the top of our heads. There's a couple of different options. So what we're going to do is we're going to write the parentheses and leave a little blank in there. And then what is oxygen when we write it in our formula or write it in our name? How do we change it? Oxide. So this is going to be iron something oxide. So we have to figure out what's going in the parentheses. So we do a little bit of math. What charge does oxygen normally form when it's an ion? Yeah, it's in 6A, and so it's 2 spots over from the noble gases, so it's going to be a negative charge. So oxygen is going to be 2 negative. And we've got 3 of them. So 3 times 2 negative, we have a total 6 minus charge. We also have our iron. We've got 2 of them. We don't know what the charge is. We'll write in an X. And what's the total charge need to be for our iron? Our total positive charge needs to be what? Needs to be 6 plus to balance out the 6 minus from the oxygen. So we need something that when multiplied by 2 gives us 6 plus. What would that be? It's going to be 3 plus. So this is going to be x equals, we'll do the whole thing, 6 plus over 2, which is 3 plus, so iron 3 oxide. This is one of the names. We also have the common name version, which would be ferric oxide. So our stock naming and our common naming. Iron 3 oxide, ferric oxide. On the nomenclature worksheet, you're supposed to provide both. On the exams, you're probably just going to see the stock notation. You might see either or be expected to provide both on an ions quiz or on the nomenclature quiz. All right, so we're going to name some compounds. We want to name the compound PbO. Pb is what? Peanut butter. It's thick, it's chewy. Lead is also thick and chewy, I assume. Don't chew it, it's bad for you. So Pb is lead. Do we know what charge the lead is going to be? We don't know what charge the lead is going to be. That's one of the ones that could have multiple charges. It's going to be lead something, and oxygen, we saw in the previous example, we take the base, ox, and we add ide to the ending. Now it's up to us to figure out what goes in the parentheses, to figure out what charge it is. This one's a little easier than the example slide. We've got 1 Pb, we've got 1 O, oxygen's still a 2 negative, it's always a 2 negative. We've got a total of a 2 negative charge. What charge do we need for our lead? We need a 2 plus, so it's lead 2 oxide. The other name, plumbous oxide. Okay, then go ahead and try naming the compound Cu2S. All right, what do we have for Cu? Cu is copper. Do we know what charge it is immediately? Probably not immediately. And then the sulfur, the S, we take the sulf base and we change the ending to ide. Now we need to do a little bit of math, figure out what the charge is on our copper. We've got 2 Cus. We've got 1 sulfur. The sulfur we know is a 2 negative charge because it's in the 6A column, just under oxygen. We've just got one of them, so it's an overall 2 negative charge. To balance that out, we know copper is going to have some sort of positive charge. 2 times whatever that positive charge is on copper has to equal the opposite of our 2 minus, which is 2 positive. You can probably put together what the X is going to be. It's going to be 1 plus. So it's copper 1 sulfide. Or I believe this would also be cuprous sulfide. Questions on those? Okay, and then this is where the oxyanions come in the lecture slide order. So the oxyanions, remember these are the ones that are on the green sheet. We just talked about them at the end of last lecture. We would work on memorizing the ATE endings. They have systematic naming, so it's going to be the base of whatever the other nonmetal is. and then the ending is going to be ATE or ITE. Those are the two options. It's only those two options for the endings. The 8 form is the one that we memorize. The ITE is one less than that, so take one of the oxygens off. The charge stays the same. We can also add one. On top of our ATE form, we can add another oxygen. So instead of ClO3 for 8, we add ClO4, still with a 1 negative charge, and we add the per prefix in front. We can also subtract 1 from our ITE ending. So instead of ClO2 minus, it's ClO minus, and we add the hypo prefix to say we took off 1 more. For these oxyanions, you just write the name. So instead of where we wrote like sulfide or oxide, it's just the name of the oxyanion is what you write instead of sulfide or oxide. So here are some examples. This is about as complicated as they'll get, for ionic compounds at least. We would also have to work in the opposite direction, going from names to formulas. We'll have that on our nomenclature worksheet, I believe. So we want to name this compound CrCO2. Cr is chromium. Chromium is one of our transition metal elements. It shows up in that middle rectangle on the periodic table, so we don't know what the charge is going to be since it's not zinc or silver, Zn or Ag. So chromium, have to figure out what the charge is, and then we have to figure out what's CO2 as an ion. So the CO2 ion, we would be looking on our oxyanion table for the oxyanion that has carbon in it. Find the oxyanion with carbon. On our green sheet, the one that we would find in that table is CO3 2 minus, which is carbonate. Is CO3 what we have? Do we have CO3 in our question? It's different, right? How is it different? How does the number of oxygens change? We lost 1. So from the 8 ending, which is what we have, carbonate, going down 1 more, that's what we have. How does our ending change? Yeah, it goes from 8 to ite. So CO2, it's still going to be a 2 minus, which is helpful for us in a bit. This is carbonite, which I believe is what Han Solo was stuck in. So carbonite. So now we can add in the carbonite part. We did our little bit of sleuth work to figure out which oxyanion we have. Now we have to figure out the charge for our chromium. So we'll do our little table. We've got 2 CO2, 2 minuses. So 2 times 2 minus, we've got a total of 4 minus. We've got just 1 chromium. So what does the chromium's charge have to be to balance out the 4 minus? It's got to be a 4 plus. It's equal and opposite. So this would have to be chromium 4, which is IV, not IY, IV in Roman numerals. And they don't believe that we have a common name for chromium 4. So it's just chromium 4 carbonite. I'll work us through the CONO3 as well. So we've got CONO3, CO, big C, little o is cobalt. We don't know what the charge is going to be because it's one of our transition metal elements. So it's got a couple of different options. And then for the NO3, we would look on our green sheet, or we'd have it memorized. The nitrogen oxyanion that looks like NO3 is NO3 minus, and that is nitrate. Nitrates show up in like preserved meats. They're also important for soil. They're a food source for plants. So cobalt something nitrate, because that oxyanion perfectly matches. And then we get to do our charge balancing, and this one is also relatively easy. The NO3 minus has a total 1 negative charge, so the cobalt has to have a 1 plus charge. So cobalt 1 nitrate. Any questions about any of the examples that we've gone over? So this is one of our categories. It's arguably the biggest category. I think ionic compounds is about the same amount of brain power and material compared to molecular compounds, which is our other one, the next one that we'll cover. And then acids is bigger than molecular compounds, but less than ionic compounds, I think. If you're thinking to yourself, this is a lot, yes, you're correct. It is a lot. It needs to be this way, unfortunately. It needs to be this exacting and this exhaustive of a naming system because of the billions of ways that we can combine all of the elements. We have to have a system where the name cobalt-1 nitrate refers exactly to CONO3. The name chromium-4 carbonate refers exactly to CrCO22, and it can't refer to anything else. That's why the naming system is so rigid and it's got so many little details in it. If you get good with doing the nomenclature, it'll make the rest of the class a lot easier. So I'd recommend spend a considerable amount of time studying the nomenclature stuff. It shows up heavily on the next exam. We also have a quiz on it after our exam too, and we're going to continue using it throughout the rest of the course, just kind of as an assumption that we know it. So it's a lot. It's manageable. You can do it, but it's going to require you to study outside of class, do extra problems, do the nomenclature worksheet, review, and make sure that you're staying caught up and on top of it. Great ways of doing that: going to Logan's SI sessions, going and hanging out with the people in the STEAM room in the library from noon to 5, Tuesday, Wednesday, Thursday. And you can also ask me in office hours or anytime, really.